Okay, so tonight we're going to do something a little bit different, a bit of a mind-bending little trick we're going to do. So we got the Earth here. So imagine we get a piece of rope. So we got some string here. This will represent the rope. And what we're going to do is we're going to take the rope and just imagine the Earth is completely flat, and we're going to lay the rope down along the equator of the Earth. We're going to go right around the equator, and it's going to be perfectly flat with the Earth, and you will not be able to put like a millimeter in between the Earth and the rope. So imagine that it's completely flat all the way around the equator till you get around to the other side. There we go. So then what we're going to do, so you cut the rope, tie it there. What we're going to do is add 20 meters to the rope, which you must admit is very small. The circumference of the Earth is like 40,000 kilometers. And I've actually got this here. I looked up the circumference of different planets, and it's 40,075 kilometers. So there we go. So 20 meters isn't going to be very much from 40,000 kilometers. So imagine we've added 20 meters of rope. I'll get this out of the way for a sec. Added 20 meters of rope, and we've done the same thing again. Added 20 meters of rope, went around the circumference of the Earth at the equator, right around. And then what we did, we tied that there, tied the ends together. And then what you did was you get like 1 million of your friends and have them all together. Sorry about social distancing here with COVID-19, but they've got to be all together for this experiment. And then they lift a rope up off the ground until it's nice and taut all the way around, really taut, like not even like a millimeter. It's got to be like following the curvature of the Earth right around the whole Earth, but really taut. Not stretched, just taut. So there's no difference in length. You're not stretching it, not compressing it, just nice and taut and absolutely parallel with the equator, going all the way around, completely flat, like perfectly flat. Now my question is, how high, when they lift the rope to make it completely taut, and you go all the way around, how far off the ground will 20 meters of extra length of rope around the entire Earth, 40,000 kilometers, and you're just adding 20 meters? It's just like the length of my house here. And you imagine how small my house is compared to all the Earth. How far off the ground will they have to pull the rope until it's completely taut? It's going to be this high? Well, that seems too much, doesn't it? It'd have to be very small. It'd have to be like millimeters. It'd be less than an inch off the ground, wouldn't it? That's what you think, don't you? But I'm going to show you that it's actually a lot more than that. In fact, your friends won't be able to, even reaching up, even if you had tall friends, even 6-foot friends, 7-foot friends, I don't think they're going to be able to get the rope taut again. It's going to be quite high. And I'll show you exactly how high your friends would have to lift the rope up to get it taut again when it was completely taut on the equator, completely taut, perfectly smooth, and they lifted the rope up to get it taut again. It was the perfect curvature, followed the Earth perfectly. I'll show you how many meters high they'd have to lift the rope to get it taut again. So let's get these windows back up again. We've got the Safari browser showing the circumference of the planets, and also we've got my calculator here. So I've done the calculations for us here. So looking at the circumference of the Earth, we've got 40,000 kilometers, so we're going to convert to meters. So it's 40,075 meters. Alright, but before we do that, I'll show you the calculate, how we're going to do the calculations. So what we're trying to do is work out what the increase in radius is when you add 20 meters to the circumference. There's a little question marks there. So your circumference equals 2 pi r. So basically we're looking down at the Earth from the North Pole, and it's cut through, and we're just looking at the equator, and it's going to be perfect circle. not like I've drawn. It's going to be a perfect circle, and we're looking down there, and so you work out the circumference is 2 pi r, so therefore the radius is the circumference divided by 2 pi. Okay, and then we can work out the difference in the radiuses here when we add 20 meters to the circumference. So I've done the calculations here, and so we've got 40,075 meters. You work out what the radius is there, and it works out to where are we here? 6,378,134.3444077056 meters. That's the radius. So the next line, we're going to add 20 meters to the circumference. So that's what we're doing, adding 20 meters of rope. So it's going to be 40,075,020 meters of rope. So you divide by 2 pi again to get the radius, and you get that big number there. Then you just take the radiuses away from each other, so you see the difference in radius, and it equals 3.1831 meters. That's incredible. That is actually, I did the conversion, it's 10 feet 5 inches. 10 feet 5 inches. So your friends, even if they're very tall, even if they're all basketball players, and we had millions of basketball players, I don't think they'd even be able to, just standing right there, they wouldn't be able to lift it up high enough to get the rope taut again. And the amazing thing about this is, it works with any radius. It works with any size planet. Any size planet you got there. Add 20 meters to the circumference, and you will always increase the radius by 3.1831 meters. And I'll prove it to you here. So what I'm doing, we're doing it a different way. We're going to work out the circumference. We're going to work it out the difference in radius. So we'll have a fixed radius of 1,000 meters. So you go 2 pi r. So 2 pi times 1,000, you get 6,283.1853 meters for the radius. And then we're going to add 20 meters to that radius, and so we get as 6,303 blah, blah, blah. And then we're going to divide, so that gets raised, and we're going to divide by 2 pi. So when you add 20 meters and divide by 2 pi, you get 1,003.183 meters. So you see there, it's the same number. You're just adding 3.183 meters to the radius. And I'll show you here, you can do it for 2,000. Just keep going, you can just plug in all the numbers. You're always going to get 3.18309, so 3.1831 roughly. And it's the same number, it plugs out every time you do it. So there we go. I think that's pretty incredible. When I read it, I thought, this couldn't be possible, and I actually did the calculations. It's absolutely correct. That is what you get. Add 20 meters to any circumference, and even if it was like a small ball, you add 20 meters to it, it's going to increase the radius by 3.18. What was it? 3.1831. 3.1831 meters. There we go, guys. Hope you enjoyed that one. That's my little trick for today. Little brain teaser. Show it to your friends. See if they get the right answer. I don't think anyone will get the right answer unless they're little geniuses. Yeah, I thought it was amazing. So I thought I'd share it with you. I've got a whole lot of little mind-bending tricks, card tricks, all sorts of things that whenever I think of a new idea, I email myself a new YouTube idea. I've got a whole backlog of YouTube videos I want to do in the next few months. So stay tuned. Don't forget to like, subscribe, and share. And I'll see you next time. Cheers.